Okay, everyone, welcome to this first seminar talk of this week. Our speaker is Pavel. By now, everybody knows him, and his entire pedigree is right there. So I'll just hand over.
Thank you, and first of all, I would like to thank organizers for kind invitation to this program. I'm really happy to be here. I'm not sure that already, for now, everybody knows me, but at least some of you who see me first time, hope you will have some glimpse of my research. So my goal is to give introduction to the subject and some focus on some areas, while our talks will be into our workshops. So I will try to make minimum overlaps, and so I hope this talk, I try to do it reasonably early, will give you some impression what I'm doing. I'm highly interested to talk about that in more details. So please come after talk, any time in the future, come and let's talk. So because I'm given some review, there are plenty of collaborations, many of them numerical, and perhaps some of collaboration results I will not manage to mention today, but let me mention among them my former graduate student Sergei Dichenko. He is now, how it's called, acting assistant professor, how we call University of Washington, just moved there, and now my Sergei Dichenko, it's different Dichenko, and my another former graduate student Denis Silantev, he is now a postdoc in Courant. So I will be talking about ideal fluids. Ideal means no viscosity, and so we start just from Euler equation for velocity v, density rho, pressure P, and acceleration due to gravity, and we assume incompressible fluid. So it means this rho we later just replace by 1. It's incompressible and homogeneous fluid. Now for ideal fluid, if we start from potential flow, it means that if we introduce velocity potential for V, we call this phi is called velocity potential, then will flow remains potential for a while. Not for a while, forever. And I will look exclusively on this case. So then our incompressibility condition immediately means just for potential flow, just Laplace equation inside fluid. And second equation for this type of flow, we can factor out nabla, and inside square bracket we'll have just Bernoulli equation. And basically for ideal fluid we need to solve Laplace equation inside fluid, and Bernoulli equation is sufficient to solve only on boundaries. Now my major focus will be two-dimensional flows with free surface. So for example, typical situation, we have ideal fluid, free surface with red line, and above that we have vacuum, free space, whatever, or in applications, for example, for air over water, if we're looking for large waves, then it's usually, and winds are not strong, then our approximation of free space works quite well. So, and two-dimensional flow means situation like shown in this picture from ocean in ocean swell, when we have parallel waves, so third dimension much less important here. So in this two-dimensional settings, x horizontal coordinate, y is vertical coordinate, alpha is the surface tension, and simplest way to describe shape of surface in this case is what is sometimes called natural parametrization, when y is a function of some function eta of x and t. So for each x we have some surface coordinate. But this works when we don't have overturning waves. If we have situation like this, then natural parametrization will not work out, because for some x we'll have more than one solution on this vertical line, right, for free surface. In such a case we need to switch for more general parametrization. So basically x and y will be function of u, and we also depend on time. So it's really time-dependent parameterization, and u, for example, we can prescribe runs between minus and plus infinity if we're looking for infinite space. And now let me define boundary conditions. So I start to have introductory description, start a little slow, what a boundary condition for natural parameterization before switching to more general one. So one way to describe that is that total derivative over time of this eta surface elevation, which is obviously partial derivative plus advection term, equals to vertical velocity v sub y. Then, for example, if we now solve this equation for partial derivative, right, for this vy, then this right-hand side can be represented as a normal velocity times this obvious factor, basically Vn. We introduce unit normal vector outward looking compared to fluid, so it's just defined by this expression, just derived from our parameterization of fluid surface, and when we project on this normal direction, we get this extra factor just from this denominator. So this alternative expression we will use later. This is why I'm spending time on it. So basically what this kinematic boundary condition tells that in normal direction, free surface move with fluid. So if you look for some fluid particle on free surface, then fluid exactly moving. So if you have fluid particle somewhere here, it's exactly normal direction moving this way. While tangential direction does not change of fluid surface, so for ideal fluid it's not important. And second is dynamic boundary condition, eventually comes from Newton equation, which tells that if we have outside of a fluid pressure is zero, or we can set it to any desired constant, but typically zero is simplest choice. And when we move just from outside with zero pressure to just inside, there is a pressure jump, which comes from surface tension, and this is exact expression for it. I remind you, alpha is surface tension coefficient. And this pressure jump we just plug in into Bernoulli equation, from which we're interested, as I already mentioned, just on the free surface. So basically from this point, we're not interested about pressure anymore. They do not show up from the dynamical equation. Although if we need pressure from in deep inside fluid, we can always use this equation also inside fluid and recover pressure. Now, and at infinity, we have just decaying boundary condition. As usual, phi is just potential. We can also set to go to any constant, but simplest way, because later we differentiate, right, to recover physical velocity as a number of phi. So in principle, it could be any constant, but simplest way to just to set it to zero. So decaying boundary conditions. Now the same stuff for general parameterization. Well, here it looks a little different, because here I just basically take this velocities of fluid particles and project, so this is time derivatives, projected normal velocity, again equals Vn, which I defined before. In this case, unit normal vector just has this general expression. This is what we teach in undergraduate vector analysis course, so this is absolutely simple expression. And now what will happen with dynamic boundary condition? This is more general expression reduced to previous one, just as a particular case, but now we're not restricted to single valued parameterization. So arbitrary complicated behavior like this is allowed for us for this for more general parameterization. But why I stress so much this more historical natural parameterization, eta? Because first of all, yeah, before that, let me mention that Laplace equation inside fluids plus kinematic and dynamic boundary condition form a closed set of equations. But again, if we restrict to natural single-valued parameterization, there is a well-known result of Vladimir Zakharov from 1968, and this paper received many thousand citations since when it's widely used in the field, that we can introduce canonical Hamiltonian system for two variables, canonical momentum psi. This is nothing more than Dirichlet boundary condition for phi, and with eta natural parameterization of free surface. So what's a Hamiltonian H here? It has absolutely transparent physical meaning. It's just sum of kinetic energy K and potential energy of fluid with free surface. So for example, kinetic energy, we just integrate half square of velocity over entire fluid volume. And here for generality, I assume that we can work either in two-dimensional or three-dimensional space, because this canonical structure also works in 3D. So basically, I assume that R it's x and y, and x it's either it's either if in two-dimensional flow is a scalar or it's two-dimensional vector if we have two horizontal directions. So until some point, this Hamiltonian formalism will work for both cases, and when I separate, I will focus on two-dimensional flows. So basically what we can do with integral, of course, we can represent for single value parameterization, just integral over one column of fluid from minus infinity to free surface, and then integrate over horizontal coordinates. Now, potential energy, it's immediately written in horizontal coordinates, basically this term. So we grab, let me grab some piece of chalk. If I will find one. Yeah. So if this is free surface, we just grab some column of fluid like this, integrate over vertical coordinates, so we have 1/2 of height. And then we just integrate over all this column of fluid, so we get this potential energy. And for gravitational potential energy from surface tension, it's now absolutely transparent physical meaning. It's just total area of the fluid minus 1 to have 0 energy for unperturbed fluid. So absolutely general expressions, no restriction except its single valued parameterization. And now next thing to do to convert this integral to surface integral. Another undergraduate exercise, for example, let's take kinetic energy. So we have this previous expression, and then we can just move null to outside, right? Because if we differentiate, Laplacian is 0, so this identically close to each other. And then, of course, this is immediately in conditions of divergence theorem, so we switch to surface term. N is again unit normal vector, and this is ds element of surface. So this part is just gives Vn times Vn times psi, which is just value phi. I remind you, just Dirichlet boundary condition. And then we switch from ds to dx, so integral over horizontal coordinates. Of course, we have this factor from unit normal vector. Now, plugging into Hamiltonian, two other terms were already written from very beginning in R variables. Oh, I apologize, it should be x with two-dimensional variable with both x. And we have surface integral. But the trouble is that we don't know normal velocity. In a sense, it's not expressed in terms of canonical variables psi and eta. So we have to do that. This is why we don't have full solution of this problem. But now let me try to convince you that this statement made by Zakharov in 1968 indeed is working. So let's calculate variational derivatives, so functional derivatives, to make sure that these equations are equivalent to original Euler equation. So let's, for example, calculate this variational derivative. So here only this kinetic energy term from Hamiltonian depends on psi. So here, obviously, because we can do divergence theorem to apply any of these two terms, so they're equivalent. So we will just apply to this psi and remove factor 1/2. And then, of course, we get this expression, and then we immediately realize it's nothing more than our kinetic boundary condition, right, in the second form, which I showed before. So our first equation we check. Indeed, it's working. For second equation, we need to do, we check second equation. For first equation, this one, we need to do a little more work. So here we need to calculate separately for different terms. Or for example, for variational derivative of gravity terms, of course, it's super easy. For surface tension term, yeah, we also just play a little bit with integration by parts and produce this term when we calculate variational derivative. And now, but we have a little more trouble with kinetic energy. How we handle this? Because again, we need to find variation of Vn, normal velocity, over eta, over our surface parameterization. And trick is the following: to calculate this variation, we switch back to volume expression instead of surface expression. So I remind you, from this expression we go back to this expression and now calculate variational derivative of this. And there are two contributions. One contribution when we just directly look for variation over this limit, right? So in this term it immediately just kills all integral, we have just half of square velocity. While there is also contribution to phi when we move surface, when we move our surface, vary our surface. So basically I move now this to here and we need to calculate with delta phi. Now at this point it's convenient to switch from this form back to surface variables. So we have exactly the same term as previously. Basically instead of phi, which becomes psi, or we have now delta phi on free surface. Now here what we need to immediately realize that if we shift our free surface by some delta eta, it's equivalent that when we arrive to point y, what was before, so basically we take our phi initially at point y minus delta eta, and on a shift it's arrived exactly at point y. So in this variation we have just this minus term. It's extremely important. If you're not careful about that, we get wrong answer. Okay, so basically it corresponds that we just vary free surface and without changing form of phi, we just translate fluid and produce this expression, which after that we evaluate just on the free surface. So let's now bring together all previous terms which I calculate for this variational derivative. So we have these two terms I mentioned before. We have this half of square of velocity, and this term comes from this. So this basically, this is what we have from here. Now we don't need to calculate this term directly, which we can still do through kinematic boundary condition, but there is no need. We just recall this kinematic boundary condition and now realize that original Bernoulli equation, because what I want to show that this is equivalent to Bernoulli equation. But Bernoulli equation, it was in variable phi, not psi. Remember, psi is just Dirichlet boundary condition. So calculating this partial derivatives, just obvious change of variables, so we differentiate over partial derivative over phi and partial derivative over this argument by chain rule. So we produce this obvious expression, and this is d phi dy shows up exactly as here. So we will see that it will be exactly the same term if we notice that d eta dt is just this, right? So this is exactly equals to this. So then combining all these terms together, we just recover Bernoulli equation if you just recall that this is pressure jump. So complete equivalence, we obtain canonical Hamiltonian system. But you see, there are some things happening when you do variation. You need to really do it carefully, because it's still it's hidden here that we solve the Laplace equation in a depth of fluid at each moment of time. Now, how we generalize this stuff?
Could you remind us what capital psi is?
Psi is Dirichlet boundary condition for phi.
Okay. The surface value of the potential.
Yeah.
Okay.
Exactly. Yeah. And please feel free to ask me more questions. I will be happy to clarify.
So
And he also can give-
yeah. Although that's quite a complicated derivation, is it possible to say the answer must come out that way? Because the pressure as an internal force, it's kind of it balances out. It does no work in a virtual displacement. So can you
Yeah,
see in
but-
advance it simply must come out that way?
Yeah,
That's how I
exactly,
tend
yeah.
to think
But
of these things.
basically, it's not obvious from very beginning. You know, some memory about Hamiltonian structure of equation, because Euler equation originally is Hamiltonian. It must be saved, but it's not guaranteed that, for example, it will be a canonical Hamiltonian structure, and we don't know what canonical Hamiltonian variables. Basically, this, what I just give derivation, gives full answer that psi and eta are canonical Hamiltonian variables. But you're completely right, it basically eventually comes from Newtonian mechanics. More questions?
And so this so far is this what was done in 1968?
Yeah.
This is so
And now we switch to 2019
okay.
on this slide. Yeah. Yeah, but because I wanted to stress on this topic, I mean, always well known, because, you know, here people from different background, I felt that it really makes sense to refresh this, of, I'm sure for many of this it was new. Now, what's going on in 2019? So we're going for this more general parameterization, but now I restrict just to two-dimensional flow. I believe this analysis is possible to generalize to 3D, just never had time to do that. And I really focus on this talk on 2D, so it's completely sufficient. So what we can do here, for example, we can look for energy in gravitational field. So we take our domain omega. You see it's not natural parameterization, it's just domain. We allow some overturning waves, but this general parameterization covers everything. The only thing we assume that wave breaking never ends up, so we don't have holes in the water. So this is okay, but you know, these holes will not allow. So its domain is simply connected. Okay, then we just integrate just of linear gravity potential, right, proportional to vertical height, and then I subtract energy of unperturbed fluid again to have finite total energy. We are only interested about variation with respect deviations from flat surface, and then just use simple trick again of the gradient math from Green's theorem in 2D. For example, we can introduce this auxiliary function, y hat is just unit normal vector in y direction, and check that this is equals to this, and of course in this divergence form we immediately produce this. So basically for single valued parameterization, with xu we can move inside, so it will be dx, and y turns into y, we will get old result, although this result is now work for multivariate parameterization, so not a problem. I mean multivariate in terms of natural parameterization. Now similar stuff, for example, for kinetic energy, again integrate all volume. So, but we cannot do now simple stuff like what I did, integrating like this volume for kinetic energy. You know, integrating like this would be of course crazy. Instead, we just again applying Green's theorem, get this expression gamma is a boundary for normal velocity psi. Oh, here apologize. Low and uppercase psi it's the same Dirichlet boundary condition. Then again switch from element of surface into du, element of our parameterization, plug in everything into Hamiltonian, and we get this expression. No restriction, this is just generalization of previous stuff of natural parameterization. Now,
Is it obvious that those integrals are well defined? I mean, they are over infinite interval.
Well, we assume that either we work with periodic system, but typically instead of this, we assume that everything decays at infinity. So decays fast enough. Yeah, it's obvious that, well, basically, we typically assume that, for example, that our function will be analytic on a real line. And I will mention when singularity touches a real line, it might be issue with that, but we assume at least until last moment everything good. So no troubles here with non-existence of any of these integrals. But you're right, it's absolutely a good thing to check here. Okay, now let's quickly mention how we advance in time. So we have Hamiltonian equations, and here I show this one particular example of natural parameterization. Basically, what we need, assume, for example, we have initially Dirichlet boundary condition. What we're doing, we're solving at given moment of time Laplace equation, which will allow to recover Vn, it means we recover Neumann boundary condition. So in our words, we need just to find Dirichlet-Neumann operator. And then use it to advance in time, how our free surface evolved in time. So it's really dynamically evolving. So this is really a non-local problem, because at each time step, we solve the Laplace equation. Now, what we basically way to find Dirichlet-Neumann operator, we can always do this by perturbations. Perturbation, here small parameter will be typical elevation of the free surface. When it's small parameter, then we can solve this perturbatively and both in 2 and 3 dimensions. And so again, it was first time some mentioned Zakharov in '68, and more recently it was more advances in that in terms of analysis community. For example, people try to prove long-time existence of solution. Sometimes they call it almost global solution because it's basically we can prove for small initial condition it exists on exponentially large times. This is starting from work of CUO and many more recent developments. But this is not what I'm interested here. I'm interested about strongly nonlinear solutions. So basically to approach as much as possible to such situation. Of course, it's a three-dimensional wave breaking, but I focus on this 2D. This is our spectrally accurate simulation. Basically, we can resolve such situation with arbitrary precision and closer to wave breaking. But still, until moment when still our domain is simply connected. This is our hope to describe. Now, let's from now on work only in 2D. So here advantage that in 2D we can use conformal map and map our domain, fluid domain, into simple domain where we can find explicit form of Dirichlet&lt operator. So for that, I just introduce complex variable z. It's x plus iy, horizontal vertical coordinates. Now, and look for conformal map from auxiliary variable w, which is u plus iv, from low complex half plane is mapped into fluid domain with dashed area, such that real line v equals 0 is mapped into fluid's free surface. So in that case, our conformal map, it will be boundary of value of conformal map at v equals 0. It will be nothing more than just particular value of our parameterization. As usual, if you not require some conformal properties, we have infinite number of possible parameterization, but if you fix conformal map, then it will be just particular way. Boundary value again of conformal map.
Pavel,
Go ahead, yeah.
the fact that on one side of your surface you have a vacuum and on the other side you have a fluid, so that there are two different materials on the two sides, right?
Well,
Because
basically,
if I
assume here
really-
nothing, just free space.
Right. So does the fact that you have vacuum on one side and something else on the other side have any effect on the conformal map that you're studying? Is that reflected in any way?
Okay, well, this is right question. Basically, physical situation only happened here. Here it's just nothing, and basic core things which I'm doing analytic continuation into vacuum. Here we're allowed to have singularities, everything.
So your conformal map goes from blue to blue. That's what's
yeah.
happening. That's
And-
what the fluid is
And
studying.
what is happening outside, it's a question.
Uh-huh.
It's already basically a question of efficient description, but physical only with,
I see. It tells you which is the domain.
No gust, no wind outside.
no wind, exactly. Okay, now let me remind in our undergraduate stuff, usually we have this application chapters of undergraduate complex analysis book that for two-dimensional flow we can introduce stream function. I call it theta. So if here subscript just components of velocity, this is definition of stream function, and also I remind definition of corresponding velocity through velocity potential phi. So this definition automatically ensure that we automatically satisfy incompressibility conditions just from these cross derivatives. And then if we define complex potential as phi plus I theta, so velocity potential stream function, then these definitions will be nothing more than Cauchy-Riemann equations for analyticity of this complex potential pi capital as a function of complex variable z. For example, differentiating we immediately produce complex velocity. Then for our simple domain and low complex half plane, of course, we have relation through real and imaginary part of analytic function through Hilbert transform. So this is all what we can do here. In this community, of course, it's obvious for everybody. Now, immediately we realize after that, for conformal map, we just, if pi capital was analytic in this dashed area, it will be analytic here also. So here I've used notation to use the same pi for variable of z and w, and from now on I will actually use pi as a function of w. So it's not just conformal map, but it's really compatible with dynamics here. Now, I can ask question what will happen with our kinematic and dynamic boundary conditions. Well, we simplify a little bit on these conformal variables. For example, kinematic boundary condition, which I showed before, in this case, it just becomes a Hilbert transform of psi. So psi, again, is the same Dirichlet boundary condition. And because it's now simple domain, right, taking derivative is also easier. And for the dynamic boundary condition, it's a little more messy. It's not obvious that it's coming in this way. And basically, there are two ways to, again, no approximation, everything exact. So you see the Hilbert transform involved, some derivatives, here square root of Jacobian, this is involved. And one way to obtain this expression is just do all this change of variables from original Euler equation with free surface. Typical calculation, I once did it just for fun. It's typically 20 pages of calculation. But instead, if you do instead variational principle, then it's less than half page, I would say 1/3 of page. So how to do that? We recall our Hamiltonian, which I showed you before. The only thing now how I updated, I took into account that we have relation between, for example, x and y through Hilbert transform. So I instead of x, I put everywhere this Hilbert transform of y. And now I write corresponding Lagrangian in this form. Basically, there are some arguments how to write that, some experience, you just know how to do this. So then we have this temporal derivative part minus this Hamiltonian, writing corresponding action and looking for extremum of action, so just taking variational derivative and obtain these equations immediately, as I said, like 1/3 of page. But there is an additional byproduct of this, that using this variational principle, we immediately write Hamiltonian form of equations. So they now non-canonical. And I would like to pay attention again. This equation not resolved with respect to time derivative, right? There is something going on which we can handle. But before handling that, let's mention symplectic Hamiltonian form. So this Q is just y and psi, our two Hamiltonian variables. Again, we're not canonical anymore. Omega is 2x2 matrix non-local operator, and each term basically involves Hilbert transform. Well, it's all published in this 2018 paper, all details there, but basically everything exact. Main thing that it's non-local, that it involves Hilbert transform. And it's Q-symmetric, all Hamiltonian properties are satisfied. Now,
I have a question. So, in this representation, what happened to the x-coordinate?
so sorry, what?
To the x-coordinate? Because we are using the parametric representation of the free surface,
Yeah.
which relies on two functions, right? X
Yeah,
and,
yeah.
and
But
y.
because x we recover, for example, derivative through Hilbert transform of y, except we need to subtract this identity part, so it's actually minus u. I call it x tilde, I will use this notation later. Basically, x always recovered from y,
Okay.
because we use conformal map here. So we only need only one function. Second, always recovered from Hilbert transform. Yeah, it's absolutely
What is
right
the
question.
origin of this identity?
Well, it's what Hilbert derived. It's basically you have low complex half plane, and you have analytic function, and there is always relation from Hilbert transform from a real imaginary part. Basically, you draw such
Okay,
contour.
okay.
Yeah, it's Sachotsky-Plemel formula.
Sure.
What it's called. More questions? Okay. Now. Again, please ask me question. I understand people different field. For me, it's obvious, but if you're not using Sachotsky-Plemel every day, of course, it might require a little thinking. Okay, now next step is to invert this operator, because I want to solve for time derivative, which is, of course, convenient. Right? So we like this operator, and it's actually natural because it comes from rational principle. It's not degenerate, so it means there are no Casimir invariants, so we can invert again. It's some working with these non-local operators, but after some efforts you can do this, and this is result. But let me first mention that result we obtained actually in this early work of Dichenko-Kuznetsov, Spector, Zakharov. This is dynamical equations. So then non-local, but equation purely on a real line. And again, what I mentioned to Bartek, x just related to y. Yeah. And here, yeah, obviously from here it should be minus. Okay, now basically you see it's y and psi now solve for time derivative, where I Hilbert transform some Macy terms, but it's already everything on a real line. So all solution, indirect solution of Laplace equation were hidden into these non-local terms with Hilbert transform. And of course, numerically, for example, it's super convenient because Hilbert is just sine of k. For spectral methods, it's a natural thing to solve. So we really reduce two-dimensional problem to one-dimensional. Now, but this is again historically, but now we have our Hamiltonian formulation from 2019, and when we, and let me first before mention to be historically accurate. So this type of equation, equivalent equation, more or less equivalent, we obtained in number of works, starting from work of Ovsyannikov in 73. Well, let me mention Salih Tanvir, who also obtained for periodic case non-decaying boundary condition, but it's eventually, it requires some work to show, but eventually it's equivalent equation. And actually, let's see Salih here. Okay. And now Hamiltonian formulation. So basically, R is now inverse operator of omega of symplectic operator. Sometimes such type of operator called co-symplectic operator. Again, it's another non-local terms with Hilbert. All details if you want to follow in this paper, but main thing, no approximation, everything exact. But there is immediate, extremely important consequence from this form. That form of this operator, it has zero from properties of our transformation. You see, one element is zero. And now, if you write corresponding non-canonical Poisson bracket between any two functional, then will be in this form, where this is just components of this 2 by 2 matrix. We see, because we have zero here, we have only variations over y psi, psi y, and psi psi, but no terms with variations over y y. It means that if we take any two functionals of y only, they will automatically commute, which always considered to be sign of integrability if this functional will be integrals of motion. Now, let me now...
And how good they behave at infinity, these functions? You need to integrate them, right?
Yeah, well, we assume everything, we assume decay at infinity. Yeah.
So no harmonic waves.
Yeah, no harmonic. Or we can easily, when I write this integral, I can always, instead working with some period, basically with what Salih Tanvir did. I mean, he was not using any Hamiltonian formulation, but the dynamical equation was just for periodic case. So to do periodic, it's not a problem. Although physically it's more natural, you have some waves, some finite perturbation, and then it decays to infinity. So this is why I focus on this case. But again, it's periodic case, not a problem.
What is Z? Z sub U?
Where?
Sort of in the middle of the slide, Z.
This. Yeah, this is
The complex
it's
X plus.
x u plus I y u, and then we take absolute value.
With the recordments of the boundary in the transformer.
Yeah, Jacobian transformation from variable w to variable z taken at real line. Because so far we stay on a real line. Later I will extend to a complex plane. Well, I don't know, I mean, I'm moving slowly, but let me try to advance a little bit more. Now let me switch gear and show you that this non-canonical Hamiltonian structure surprisingly applies not only to this single fluid, but for more, on the first glance, more fancy cases. And one case which we will consider, it's in my recent work with our collaborator, Nikolai Zubarev, from Moscow, Russia. This is case of superfluid helium. Basically, I understand in this room it might be unusual, but let me just make major properties, which it turns out reduce eventually to hydrodynamics. Basically, this is typical experiment. We put superfluid helium at temperature, let's say 1 Kelvin. We put some heater, and then it's well known that this fluid, superfluid, it has two components. Usually it's called normal and superfluid components. Basically, heater will cause motion of normal component, superfluid move in opposite direction. So this is what is called quantum fluid. It means that basically two fluids can penetrate one through another without interaction. They interact only through fluid surface. But otherwise, we can use usual hydrodynamics to describe that. An additional effect, we also can have quantum vortices, but we assume velocity not large, so density of quantum vortices is small. Then we can neglect it. Okay.
So it's not a two-phase flow, it's two
fluids really
at the same-
penetrate one through another.
Okay.
Yeah, it's really a quantum fluid.
Okay.
But trick that can be described with some tricks by classical hydrodynamic equations. Okay, now let me quickly mention that normally this normal component has velocity, viscosity. Superfluid component has by definition zero viscosity. It's basically how all previous Nobel Prizes were awarded in the past for these fluids. But normal fluid has some viscosity, it strongly depends on temperature. And surprisingly, there are two limits when we can integrate. One limit is my old work, where I showed that in the limit of large kinematic viscosity of normal component, in some perturbation analysis, we can arrive to such system of two complex equations. So plus minus, I will not give details, basically it's function analytic and upper low complex half plane in the sense of analytical continuation from real line from U. For example, it has, of course, solution in terms of arbitrary number of poles, and Andrei showed some examples working with this. I think with real burgers, but complex burgers, my message also completely has a sense. And here what will happen, basically, if we have this viscosity, this effective viscosity, it results that if you have branch cut in without viscosity, it will split into multiple poles, moving poles, taking into account basically split in arbitrary small time take into account this term. But this is my old work from 2004, and now back to very recent stuff. I will now look on opposite limit, which happens for a little smaller temperature, typically around 1.4 Kelvin. It's already good approximation. Then we can neglect viscosity, also normal component. This is what sometimes called non-dissipative two-fluid description of superfluid helium, started from this work of Korshunov from Landau Institute 1991, but it was only linear analysis. So what we can do in this case? In this case, real good approximation, just potential flow again, except we have two components. We have velocity potential phi sub s for superfluid component, phi sub n for normal velocity. So we have again Laplace equation for both fluids. An important physical quantity is a difference of velocities at infinity. So contrary to single fluid, where we can always look for rest frame, here we generally move with respect to another in this like this. So deep inside fluid, it will be some average relative motion, and this is what I call here V capital. And I apologize, always shortage of letters. V capital sub n here means not normal velocity, but velocity of normal component. Now, boundary condition actually quite remind what we had for single fluid. For example, I showed here for simplicity just natural parameterization, although actually we work with this more general parameterization. So basically here, this time we have basically on free surface, normal velocity is the same. This time Vn is normal velocity. And this is on free surface equals also normal velocity of superfluid component. So it's usual expression as before, the only case that it's work for both components. Now, for dynamic boundary conditions, a little more tricky. It's basically the generalized Bernoulli equation as a sum of two Bernoulli terms and equals to contribution from surface tension, from gravity and surface tension P alpha. This term is exactly as previous. And we only think that infinity, because velocity is not zero, we need to introduce what is called velocity Bernoulli constant, basically proportional to square velocity. So again, this is display effect that these two components only interact through free surface and through with dynamic and kinematic boundary conditions. Now, it's possible to generalize for Hamiltonian formulation, which I showed before, to two fluids. And surprisingly, it was my very recent work, only accepted to JET. Basically, this is example of normal parameterization. We just need to take linear combination of two Dirichlet boundary conditions with one. And all terms collapses into single pair of canonical variables. Now, Hamiltonian, it's again sum of kinetic energies. It's sum of kinetic energy from normal component to superfluid, exactly as I showed before, just sum of two velocities. So gravitational energy, sum of densities, and surface tension, exactly as previous. And again, we can switch to surface variables. Yeah, here. I think I have a little mess with coefficients. Vn small is now normal velocity. Now, just quick mention about more physical picture. We can look linear analysis, and this is imaginary part of growth rate. You see here, if velocity is smaller than some critical value, it's a real quantity. This is gamma minus gamma squared. So purely imaginary oscillation, but if we exceed some critical value, we have some unstable wave numbers. Now, if we do first perturbation analysis, basically expanding around this area, then for envelope like this, we can prove that amplitude on this envelope turns infinite in a finite time. So basically, it's possible to arrive to the following Klein-Gordon equation with effective Hamiltonian. It's possible to prove finite time singularity. It means that such type of oscillations will grow in a finite time when it turns infinite, except it's a perturbation theory. That means at some point when angles of the order of one, perturbation theory not working anymore. So it's kind of natural things to do here, but question what we can do beyond perturbation theory. And it turns out there is a miracle, which I try to explain you in several minutes, that this system of two fluids, it turns easier than single fluid. So what we're doing, basically we're doing series of tricks here, which unless I would do it myself, I would not believe that they work. It's mathematical trick that they show complete integrability of these equations. Basically what I do is I switch to some effective velocity, which is center of mass, when corresponding effective velocity potential. Basically, this is this motion of center of mass, kind of weighted average of velocities. Does not have simple physical meaning, but even phi small has even less physical meaning. It's just difference of two velocity potentials. Then we just modify our Bernoulli equation a little bit. Basically, this weights chosen such way to have again sum of squares, but not new velocity potentials. And because of this definition of phi small, it has zero kinematic boundary condition. Just normal velocity is zero. While for phi capital, we have exactly as we have for single fluid, mathematical equivalent. Again, no simple physical interpretation. Then, from now on, I again also switch to 2D. For 2D flow, we can use the following trick. I can, instead of phi small, I can introduce its harmonic conjugate. Again, we have the same story that we have analytic function if you're doing complexification inside fluid, and just write instead of phi expression for psi, because sum of these squares, it will be the same as sum of phi squares, right? Just for analytic function. Then our boundary condition a little modified, because instead of zero normal derivative, you have zero tangential derivative as usual for harmonic conjugate functions. And then it's time to trick. If we now define one more linear combination, you see it's now linear combination between this weighted phi capital of effective potential and this harmonic conjugate, we obtain system which is practically decoupled. So with f plus and minus, there are two equations. They almost decoupled, they coupled through this definition, through eta, through our natural parameterization. But if we assume that f plus or f minus initially 0, then it will be completely decoupled. For example, if f minus 0, this equation identically 0, it will remain for all times and no approximation for arbitrary nonlinear solution. Now, simple physical interpretation that this f plus f minus in limit of small amplitudes corresponds to a linearly stable or unstable solution. Basically, if we, for example, choose linearly unstable solution, which will grow exponentially, and it turns out that with approximate argument, this particle becomes not exact, but it can form numerically that if even on nonlinear stage, this branch always stable. So basically, out of possible initial conditions, for example, analytic initial condition, if you just choose subclass, then out of one of two function is 0, we can construct arbitrary nonlinear solution which completely decoupled. And from now on, there is one more trick.
Quick question. What was C on the previous slide?
C is rescaled Bernoulli constant. Basically, it's V capital in rescaled unit. So relative motion of velocity of motion of fluids at infinity.
Okay.
So
But how realistic this condition that decoupling? You know, if we take phi f plus equals 0, it means that phi and psi connected very simple relations that is not probably
well,
physical.
answer is the following, that physical answer. You start, for example, from moderate initial condition. We know that one of them exponentially grow and another decay. So basically, there is dynamic selection of unstable solution, and this stable just remains small. I mean, it's not exact argument, there is no exact proof, but physically,
Right, but
no
what about
doubt.
mathematical argument? Phi and psi are real and imaginary part of analytic functions.
No, it's
harmonic
it's
conjugate.
it's a two analytic functions.
No, phi and psi. They are real and imaginary part of.
I mean, it's not classification. No, this is two harmonic functions. Two harmonic
What
functions.
is lowercase psi and capital Ps?
So,
Phi.
as I mentioned, phi capital is some linear combination of two velocity potential for original two components of fluid, and psi is complicated quantity because it was phi small, some difference between two
So they not
velocity, and then
connect-
it's harmonic conjugate. It does not, give me a second, does not have any physical meaning. I mean, transparent physical meaning.
So they no connection to the previous slide, phi and psi. Could you go back? To
Well, you can always go back, but
this phi and psi.
yeah, it's exactly this one. Yeah, I mean this one. Yeah, but now from the linear combination we construct this f plus f minus. Purely mathematical trick. I mean, it's exact. You know, I can give my life for that. It's fine because I did it myself, and of course it's double check because it's it's really a trick, but sometimes we like it. Such tricks are working. And now there is one more trick which this calculation I skip. Basically now we have, for example, we assume this. So we choose class of initial condition with 0 stable part. It gives extra restriction. So using this restriction, we can exclude one variable and arrive to fully integrable system, which is Laplace growth equation, which occurs in show cell. So which is well known, and again, it did not show up. Maybe I have to remind you to come to my talk. But yeah, I think it's time for me. I go really slowly. That its system completely integrable. It has infinite number of solutions. For example, if we go back to original physical variables, kind of rolling back all this series of transformation, we have, for example, solution in terms of logarithms for this extra variable, which if we differentiate, it's the sum of poles. And this is solution, some of them produce finite time singularity, so basically it's now in the finite time becomes not analytic on a real line. It's only Holder continuous, but still, until this point of touch, we can still work with all integrals as before. So now let me just for teaser show what happens. Yeah, and I did not mention this exact solution when we neglect surface tension. If we recover surface tension, in each time instead of such cusp, we have formation of such type of behavior, which now, what we study now. And now to finish in this remaining 2-3 minutes, which we left. Yeah, by the way, about this Hamiltonian structure, I meant a bit omit, but basically what we did on the way, which I skip many details, we use this Hamiltonian structure, which is for this reduced equation exactly the same symplectic operator as for single fluid. Except Hamiltonian now modified and it has special form, which actually physically not so transparent, but it can be derived. But let me to finish this talk, mention what we're doing for single fluid. So basically what happens, two components, very really simplified stuff. What happens when such tricks not working for single fluid? And what we're doing for single fluid, we extensively doing analytical continuation. So if we now return to single fluid RW complex plane, when we just, we're allowed to have some singularities, upper complex half plane. And what we can, for example, do, apply Cauchy integral formula and move this contour upwards, right? Then basically what happens, there is no exact proof, it's more empirical observation, that all singularities we see in upper complex half plane, again, it's non-physical plane. We're allowed to have potentially any singularities, but for analytical continuation, for ideal fluid, it's always isolated singularities, typically square root branch cuts and poles, most common stuff what we're doing. And in addition, we kind of here doing two types of analysis. One analysis of motion and types of singularities, and another is numerical stuff. So numerical idea, very straightforward, except not easy to implement. If we just represent, we can always represent solution in terms of such integral over jump on a branch cut, right? If it's isolated singularity, or if it's pole, it's just delta function. Then we just discretize such integral by sum of poles. And what we have to then to choose them dense enough to have continuous limit to reproduce, except very close to branch cut, real solution. So this is well known as a numerically extremely opposed procedure, but we have now whole machinery how to do this stable way. And this numerical part I'm going to present on this last workshop in December. But basically maybe to finish one teaser how it's working. So this is physical space XY overturning wave. So different colors, different times. And this is what happens in a complex plane in analytical continuation. There are two moving poles here, different colors, different times. And two pairs of branch point connecting to branch cut. So here you see this discretization by poles, but doing to super high precision. Sometimes we're going up to like 200 digits precision just to recover continuous limit. We robustly recover, and it's really branch cuts. And basically stuff which unfortunately I ran out of time, which I was going to talk. And maybe I will give some informal talk later, if it will be sufficient interest, how all that stuff is working for Stokes wave. So basically Stokes wave is wave propagated at constant velocity. It turns out that for Stokes wave, we in some sense can do full analysis. Maybe let's show just one crazy looking formula, and I will done on this. Yeah. So this solution for Stokes wave has a form of infinite product of increasingly nested square roots, so high C position of singularity, and here zeta is our complex variable. But it turns out that this can be fully described in terms of infinite number of sheets of Riemann surface. So basically what I expect, contrary to Heli show, to this case with two fluids, which we effectively derive, this solution for single fluids generically will be always have infinite number sheets of Riemann surface, and looking for integrability, which unfortunately I ran out of time, I did not come to integrability, will require to looking for integrals of motion and this non-canonical Hamiltonian structure on all this infinite number of sheets. So basically this is stuff which I'm highly interested in. It's a hot topic for me, and I would be very much interested to talk if anybody would be interested. And again, if it will be sufficient interest, I can give just some informal talk with some time later. Thank you. Sorry for being late.
I guess most people ask questions during the talk, but if there's one or two.
Just one. In this two-dimensional water wave model, what is the amount of regularity on the curve, on the function eta, that would reflect a realistic situation? If you're modeling a storm, so your water is gonna be pretty choppy. And
Here we
how
need to
much bad
distinguish.
can eta be?
Yeah, so basically, if there is a strong storm, very strong wind, then we need to add second fluid above. It's become, and we
So this
also
is not
doing
a
research
model
on
for a
this.
storm,
Yeah, so
then.
basically, no, in principle not necessary. If there is a storm, just there is wind somewhere else, and when just wave coming in a calm air, then it will be good approximation except last moment of wave breaking, because near wave breaking, first of all, surface tension will become important, which in the case, integrable case which I studied, there are some solution for surface tension, but we don't have full answer. And in addition, when there are small droplets like quarter of millimeter, then viscosity will become important. So for really small scales, eventually viscosity will start to regularize stuff. Yeah, but in principle, that's a question of roughness can be set, just before that formation. And generally, I expect it will be Holder continuous until moment of break.
Okay, I think we can all ask questions later, but for now, let's thank